Thanks, Paul, for that knockout introductory. It's an inside joke, guys. All right, I'm going to give a little talk about concrete splice girders. It's funny, I was just talking outside to a buddy of mine out just a second ago, and there's a lot of people that don't know what these are. He just asked, like, what is a concrete splice girder? So let's get started. What is this? Concrete splice girders, there's a misconception, or I talked to some other people in the district, and they go, oh, we've been doing this for years. This is not what we're talking about. We're not putting two pre-stressed beams, filling it with a slab and a diaphragm, and calling it a concrete splice girder. There's more to it. It's more economical. You can push the span limits further. So what is it? Well, in my mind, this is not a definition. In my mind, you can think of it as a hybrid between a pre-stressed beam and a precast segmental. Bear with me. The span lengths for your pre-stressed beams, you can get up to about 150 feet. And your segmentals, you really don't want to start using till you're over 300 feet. So this kind of fits that empty area in between there as a concrete option. So how is it like pre-stressed beams? Well, there's precast sections. The shapes look very similar to our precast beams. And the deck construction is very similar. And you still have pre-stressing strands. Okay, looks great. How is it different? Well, the splice girders have, the backbone of the splice girder is the continuity tendons that you see right there. And those are interconnected between the individual precast elements. And because this makes the whole unit continuous, fully continuous, you have more efficient section, and both your bottom and top flanges experience both compression and tension. So how does it compare to a precast segmental? Well, there's precast sections, there's continuity tendons running through both, and they're continuous over multiple spans. All right, let's look at the differences. With the splice girders, you have longer precast elements, and thus you have fewer of them. And the biggest difference is that you have multiple girder lines, whereas in a segmental, you have either single cell or a multi-cell closed box where the deck is actually part of the segment, and it's an integral part of it. With the splice girders, you can have a replaceable deck. Okay, so still, what is a concrete splice girder? Still no definitions, just here's some characteristics of it. There's going to be at least two or more beam sections. There's going to be some cast-in-place splices, and there's going to be some continuity tendons that run through the full length and act as a backbone. And in the final condition, it's a fully continuous girder system. So real quickly, a simple sketch, we're going to identify them. Here we have the 5 precast sections. There's the splices, and there's a continuity tendon. Looks simple. Where can we use this? Typically, like I said, the range between 150 to 300 feet. It's made to use as an alternative to steel. And here's a big thing. It can be straight or horizontally curved alignments. Yes, we can do post-tensioning on a curve. And it's fast. The segmental construction, you all know, it's slow. There's a lot of bringing up the segments, getting the tendons run through. With this is pretty much as simple as building a simple span beam minus the ducts. Let me go back real quick. And the other big thing is that it's really not a new technology. We're just taking different things and putting it together, and taking what we do well and putting these items together. So Bridge Division is 100% behind this concept, and it's starting to show up in Texas. We have a few projects, not Bridge Division projects, but throughout the state that have used this technology. I think approximately 3, not a lot. Florida and Colorado and California and a handful of others are really jumping on board and running with this, and we don't want to be left behind. So Bridge Division really wants to get our hands in there and set up some constant or typical use sections, sort of like we did with the TX girders. So here's our sections. We have an I section, we have a U section. We'll first look at the I section. The I section can get to a main span of 300 to 325, but that says the haunched section there. If you want a uniform section, you're looking more to 225, 275. And you may say, Nick, that's a very big range. You know, it's not just a constant overall span length. And the reason for that is because the construction process is very, it dictates how long you can go with your span. I mean, if you're spanning 300 feet, you're trying to cross something, so you may not be able to put shore towers there. So if you are starting to have to move where your shore towers are, you may not get to 300. You may only be able to get to the 225 or 270. So it's very dependent on the site. The I section, you can use it on the horizontally straight alignments. We don't want to use it in curves. We can have skewed bents. Once again, just with like any other bridge, we kind of want to limit the skew angle. There's no new issues that develop because of the splice girder, but as a general rule, we like to limit those skew angles. You can use it in phase construction. And the difference between the I section, where it kind of trumps the U section, is when we cannot put shore towers underneath that main span. The U section, which I'll talk about later, doesn't allow for that capability, or doesn't adhere to it as well as the I section. Okay, so we're going to go over a quick construction process. Now, this is not the only way this can be built. That's the nice thing. You can arrange your shore towers as you wish, but here's one example. We have a 3-span unit, and we have a shore tower here and a shore tower here, and we have no shore towers in between the two main piers. So step 1, we set the back spans. Next, we set the pier sections. Really, those can go interchangeably, just depends where your shore tower is located. Next, we pour the splices, the end anchorages, and the diaphragm. Now we set the drop-in span. And I'm going to pause right here and kind of deviate from the construction process and look at this drop-in span. There's several ways that this can be done. One, which is pretty simple, is just to use a strong back to carry the load from one girder to the other. And the advantage is that it's simple, and you don't have to really incorporate any of the construction process into your design. You just let the contractor handle it. The disadvantage is that you have to, in your design, account for that potential extra weight of that strong back. The other way is to have a built-in hanger. The advantage is, well, you don't have to count for that strong back, but the disadvantage is that it makes it very complicated as a designer to know to build a good support hanger, and it makes it complicated. The other thing I have on there, you'll see like the larger moment arm. You're like, what are you talking about? Well, if you have the pier section with a cantilever, and let's say you're having it cantilevered out 25 feet. Well, if we go back and look at this at the strong back, if that strong back's about 5 feet, you're taking your point of load 5 feet closer. So now your cantilever is not 25 feet, it's 20. So you reduce the demand over the pier section by 20%. And that's huge because those drop-in spans are quite large. So that's the disadvantage I put there. You have a larger moment arm with the hanger system. So in my opinion, as from a design standpoint, just assume that it's going to be a strong back. There's no need to potentially complicate the details when you really don't know that the contractor is going to maybe change his mind. We'll allow the contractor to do that, but let him take on that responsibility. Okay, so the drop-in span section is set. Our next thing is to cast the other two splices that were right there, and run our post-tensioning strands and stress it. Final step, place the precast concrete panels and build the deck. And here I'm going to stop also. In my opinion, it's really good to make sure you put all the panels across the entire unit before you start pouring the deck. Because of it being continuous, it's similar to steel, the structure's moving up, the spans are moving up and down even throughout your pour sequence. So if you can put half of that load that's not composite already onto the deck before you start pouring, you kind of limit the effects of the pour sequence. And I can explain that better after a while if somebody wants. Okay, what does the I section look like? This is our TX, or TX, well, it kind of stemmed, it'd be like an 84, TX 84, but we are calling it an STX 7 for a 7-foot girder. You'll notice that it looks like the TX girders, but there's a few differences. The biggest thing you'll see is the 10-inch web. This is to allow for the continuity ducts to be able to pass through and add a little bit more fat in the web. Additionally, you'll see that the top flange is bigger. The top flange, we feel, really needs to be beefed up to combat lateral forces when you're shipping it and moving it, and you just need a more robust top flange. The bottom flange is a little wider. It allows for 80 pre-tensioning strands if you wish. Now, we don't encourage you to fill all 80. You really just want to pre-tension it just for shipping and hauling, but the ability is there. You'll notice that there are no strands in the web, so you have to use debonding. You cannot drape the strands. We're clearing the web out for the tendons to move around. And there's the 4 continuity ducts. We are specifying 19 strand tendons. Doesn't mean you have to use 19 strands, but we don't really want you to put a tendon that has greater than 19. If so, we may have to go, the duct gets bigger, we may have to reevaluate what we're going to do with the web. So we'll like to stick to 19. And the depth is the only variable. It ranges, we have a 7-foot, 8-foot, and 9-foot TxDOT sanctioned cross section. All right, now we're going to look at section weights. So why do we have a limit of 300 feet or for the uniform constant depth of the 275? It's really all about getting the individual segments to the job site. If you have a 300-foot unit, a 300-foot main span, your overall unit's around 770. You have 5 individual elements. They're going to range around 160 feet. That's a big section to be trying to ship out there, and they're heavy. The 7-foot girder is approximately 1.5 kips per foot, and the 9-foot girder goes up to almost 2 kips per foot. So if you look at that with a segment length of even 140, you've got some huge loads there. And even the contractors are, even at the precast yards, they're kind of little uneasy about moving that just within their yard. So you kind of have to really evaluate where your route is, how you can get the segments there. And that's the driving force. Max span length is the result of shipping, lifting, and just dealing with that big weight. Okay, now we're going to look at the haunched section. Well, most of the dimensions are the same. The only 2 differences is we vary the height, and we have it capped at 16 feet. They just get too large after that. We really don't want to put anything out there larger than the 16-foot limit. And additionally, you can increase your bottom flange. You would do this over the pier section so that you can add more compressive capacity to your section. The compressive forces in that bottom flange get really high due to the construction stages and the post-tensioning. So one option is to beef it up. So the weight governs. Yeah, the max segment length is 90 to 120. If you're looking at a 300-foot haunch main span, your pier segment is going to be about 120 feet, and that's just big. And you'll probably have a weight close to 160 tons to ship it. So that's kind of how we capped it at that 16. So now we're going to look at the I section. We're going to look at the splice detail. And I thought it was important to look at the ways that the splice can be made. There's 2 different methods. One method is to have a uniform cross-section, meaning we have a constant 10-inch web across the splice. And I'm going to start with the disadvantages first. It's more detailed to form that splice up in the air. You have to deal with the offsets of the bottom flange, the top flange. Keep in mind, you're doing this up in the air. Secondly, you're trying to connect those ducts right up there. So if you have misalignment and you're trying to make the splice, you don't have as much tolerance to work with that web. And you'll see here we're showing galvanized ducts. We're kind of leaning towards potentially, we don't know for sure, but mandating only using plastic ducts. Well, if that's the case, you're going to have a plastic coupler in there as well. That's going to take up some room. And finally, you have a strong possibility of not getting great consolidation in that bottom flange, mainly because it's difficult to get to vibrate. A lot of times contractors want to use a stinger. Well, we don't want them to do that. You have a 10-inch web with ducts, a 4-inch duct in that web. We don't want the contractor to be putting a stinger by that duct, where we have no way if he's going to mess it up, no way to know if he's going to mess it up or hit it or damage anything. So if we don't allow a stinger, then he's going to have to use an external form vibrator. And keep in mind, he's up in the air trying to do this. So that's a big disadvantage. But the advantage is that you have a nice, clean finish in the end. Well, that's kind of up to the eye of the beholder, in my opinion. The other way is to taper the web. You basically would make the web wider. You make it the width of the bottom flange, and you have ample room to make your splices. You can kind of see in a plan view right here what I'm talking. I went back. You can see right here the web feathers out in plan. You can kind of see a little rendering of it there. The advantage is simple to form. It's just a rectangle. There's nothing complicated. You don't have to worry about the consolidation. You have more room for the couplers. And ultimately, you have a higher probability of a quality splice. And that's what we really want. Now, in the future, and Graham may yell at me for saying this, but if we eventually start allowing self-consolidating concrete, maybe we'd look into encouraging the 10-inch splice. But right now, I'm all in favor of this. The disadvantages is you do significantly increase the lifting weight of that precast segment. And I have on there more detailed forming in the precast yard, but the precasters really don't care. From what we've heard from them, that's not a big deal. And then finally, the negative for it is that you produce a knuckle. That's, like I said, that's in the eye of the beholder. I don't have a problem with it. Maybe I can hang a medallion on it or something. U section. Now we're going to jump into the U section. The main span's roughly 280. You're really pushing it at the 280. The advantage of the U section is you can use it on curves, horizontally curved construction. There it is. Okay, larger girder spacings. We designed a project in Freeport. I believe it was roughly 60 foot wide, and we had 3 girders. So you can get by with less girders. As I said before, it's hard to build this type of structure without having shore towers in the main span. And this results for their much larger, even larger lifting weights than the I section. You really can't get much of a cantilever across that pier. Your cantilever is pretty much limited to about 10 to 15 feet, and you're really asking it to do a lot. So if you really need those shore towers in the main span. And it requires additional construction steps compared to the I section. And we'll go over those. I'm not going to go through the whole construction process again. I'm just going to kind of highlight how it's different between the U section. So there's additional post-tensioning stages. These result from 2 main issues. The shipping lengths of these girders are much smaller, so it turns out that you potentially have your splices pushed to where you really don't want them. They're not in the flexion point. They start to get out closer to mid-span. So you have to run some tendons potentially right there in the bottom flange just to beef up that splice. And like I was saying, if you're trying to make it cantilever over that pier, you have to add some additional post-tensioning at the top. So that's one additional step. Secondly, if you're building the U on a horizontally curved section, you have to make it a closed box even before you stress the continuity tendons. You really need to set your individual elements and make it a closed box. So you have to typically this is a precast panel and a little cast-in-place closure. There's rebar that sticks out through here, and we can show you details for that too. And that stiffens it, makes it a closed box, and you can move on. And lastly, at the diaphragm locations, it's a little more intricate because we need to build a cast-in-place, essentially inspection hole, so that we don't know if we're ever going to inspect the inside of these U-beams, but we don't want to limit it. We have to be able to crawl through the entire structure. So what does the U-section look like? We'll go over some of the key points here. It once again has a 10-inch web. We have 8 post-tensioning tendons. We have some bottom tendons that I think the precasters will actually use a pre-stressing strand is what I imagine that it'll go to, but really those are for shipping. And we have a 6 foot, 7 foot, and 8 foot depth. We really don't want to be pushing these anything larger than that because you'll see right here, they're heavy. Over 2 kips per foot. So if you're looking at your segment length of 90 feet, you're somewhere between 95 and 130 tons. And that's just a lot of load to get down the road and get lifted up there. Okay, the U-section splice. There's really one way to do it. I mean, it's not all the splice stuff happens internal of the U, so from an aesthetic standpoint, there's really no difference. But some key elements you'll see, we widen the web, we thicken the bottom flange, and we close up the top flange. And additionally, we have some shear keys that are in there to transfer the load at the splice. So research that's been done. So far we've done 2 research projects. Dr. Husty's group did the first one, 6651 here at A&M, and Dr. Barak did the other one at the Hippie College. And we'll look at 6651. No, Dr. Barak's not a hippie. He's a great guy. I love him, but the college. Okay. Dr. Husty's group really was focusing on implementation. Where can we use this? What spans can we look at? How do the precasters feel about it? And so they did the synthesis study, and they also did some preliminary design, seeing how far we could stress our current TX70 out if we were to use that shape. And also looking at failure modes at the splice. They tested it at locations of high shear, low moment, low shear, and some with high shear and high moment. And then Dr. Barak is really looking at the splice and looking at the differences, how the splice behaves in shear, looking at the plastic versus metal duct, which I think they kind of wrapped up, but I won't give you the results of that because I don't want to step on his toes. And also he's now looking at the shear capacity that involves the couplers. Engineering software, you really need something that can capture the time-dependent effects as well as the stage construction. You need to be able to capture where you're putting temporary shore towers and the removal and addition of them. And there's a couple listed there. And I can probably take a couple real quick questions because I went long, I think. Yes, sir.
Do you anticipate this being a cost savings or a time savings in construction, both initially and in the future?
Okay. The question was, is this going to be a cost-saving construction in the future or now? Well, we don't have a lot of data points to look at in Texas, but the one that we do was Sylvan Avenue. And I looked at the bid codes last week, and okay, our pre-stressed simple beams, we build those for about $70 per square foot. And looking at the steel, you're about $125 per square foot is the stats I was looking at. Looking at the bid tabs for Sylvan, they did it at $106. And we do think it'll be, we're not trying to knock out steel, we're just trying to give another alternate. Sometimes, depending where you are, steel isn't the best option. If you're on the coast, we really are trying to get away from using steel structures on the coast, or it kind of just depends. But as far as speed, it's, like I said, it's doing a lot of things that we already do with concrete, with the precast elements, the PCP panels. We're not really adding additional labor. It's really just the splices. So we think that it will be pretty fast. Anything else?
I think we should call
You got one. You
got one more?
Real quick, last one.
Why do the girders work on curve spans, but not the eye girder?
So the question was, why are the U-girders work on curve and not the eye girder? Anytime you are designing on a curve, you have torsional effects. The structure wants to twist. And the best way to resist torsion is to have a closed box. Like if you look at any curved segmental, it's it's a closed segmental. And you know, as soon as you start to get to sharper curves with steel, you jump up to a tub. It's a phenomenon of the shape, not really the technology. I mean, if you just look at a pre-stressed I-beam, there's a limit to how much you can curve those. Well, we build them on tangents, essentially, chords, I should say.